All right. Well, it is my pleasure to introduce our former student here, Daichi Hiramatsu, who almost everybody knows anyway. So yeah, he worked with us uh, and did his PhD, and in the process got a Springer Thesis Award for one of the best PhD theses. His research was also picked for the University of California system, the best research that 2021 or something at UCSB out of all of UCSB, and then one of the top 10 research things in the UC system. And he went on, and that was for electron capture supernova stuff that was in Nature Astronomy, but he also had other great work. And then went on to Harvard CFA, where he's worked with Ido Berger there for a few years and has done equally great work over there. And he's about to start off on a new adventure, which I think he'll tell us about.
That's a spoiler.
That thing, Daichi.
Thanks. Yeah, thanks for having me for the seminar. It's my pleasure. Always really nice to come back here, especially in the around this time when Boston is still cold. So I really love the weather here. So I'll be talking about how you can use supernovae to study the massive stars. So the massive stars are the progenitors of these what I say core club supernovae. I'll tell you in a minute. But as Andy mentioned, my my pointer is not working. Oh, there you go. So I think probably many of you have seen this game. I think that was only a couple of weeks ago. And then this is like last 0.8 second of the game. And that guy grabbing the ball. And then that's me. Like I gotta use Astro attacking position. So yeah, so I'll be moving there in the coming fall or the spring. That's still in negotiation, but I'm going there. So yeah. And then, you know, it's really based on that, really great work that was enabled by the LCO network telescope. So I really want to thank you guys for, just having this amazing network of telescopes and operating it. So, all right, let's go to the science. So this is the science. I'm going to start with the standard stellar evolution and then how you can, find how you can observe these transients and how you can model them. And then going to the main topics of using supernovae to study the, massive star evolution. I'll talk about the detailed case study, this really nearby supernova in M101, and then the largest sample study of interacting supernovae. And then I'll just finish with what we can do with the coming golden age of time domain astronomy. So let's start with the standard stellar evolution that, you start from a star cloud, like here. So this is where you make stars. And then if you make a Loma stars, in this talk, I mean anything less than 8 solar masses. So these might be high mass stars for some of you, but to me, it's still a low mass star. And then it takes roughly 50 million years or more to get to red giant. That's after the helium core burning. So there you have a CO core, but since the mass is not heavy enough to burn any further in the core, so you essentially just start lose the outer envelopes, and then you end up as something called planetary nebula. And then the remnant there is the CO white dwarf. And then if you have massive stars, let's say about 10 solar masses, evolution is much faster. So it takes less than 30 million years to get to red supergiants. So these stars are massive enough to burn, up to iron in the core. But since the iron is the most stable element, you cannot really burn anymore to get the energy out. So essentially the iron just collapses because of the gravity, and then the outer parts are expelled in something called core collapse supernovae. So that's the explosion that we see. And then the central remnants, depending on the initial masses you start with, could be either neutron stars or black holes. So this is the basic picture that you have in mind. And then these, anything that gets expelled in these explosions get recycled, forming these new gases and new generations of stars. So this is how the universe, evolved in like chemical elements. So, studying supernovae have really wide-ranging implications because you can actually say something about cell evolution and also explosion physics and nuclear synthesis as well, and then compact object populations. And then since this material gets recycled, it has a really huge implication in galactic evolution as well. So this is why supernovae play crucial roles in the evolution of the universe as a whole. So this is why studying supernovae, I'd say, is really interesting. So that's something, Andy's mentioned in the introduction, but my PhD highlight is actually studying something in between these two evolutionary processes. That's what I call as intermediate mass stars, let's say 8 to 10 solar masses. So they become something called supersymptotic giant branch star. It's a really long name, but what it is it's slightly heavier than these low mass stars. So you can actually bond carbon in the core. And you can, but it's not heavy enough to bond oxygen. So what you end up with is an oxygen neon core. And then you also have magnesium neon, and then this whole core is supported by the generic pressure of the electrons. And then, but if the density is right, there's something called electron capture reaction could happen. Essentially, 24 magnesium and 20 neons can absorb electrons and they emit neutrinos. And then that goes as a chain. And then since this core is supported by electrons, if you lose electrons, you lose the pressure support. So this core can collapse by its own weight. And then this is something called electron capture supernova. And this was actually predicted more than 40 years ago by a Japanese group in 1980s, but no counterpart had been observed until our work. So we published a paper, Hiramatsu and Hall and et al. So this was 2021, and then they say superstars go supernova because the progenitor is a super asymptotic giant branch star, and then it's this supernova that we studied, and then it took a while, but I finally got this poster. Hey. Nature Astronomy. So this is a gift. Oh. So I finally got this poster. It took a while for them to send it to me, but this is for you. Oh. Yeah, so this is, one of the works that I did in my PhD, and then it's definitely my PhD highlight. And so now I'm gonna come back to how we can actually observe these transients. So this is showing finding these transients, you have to run something called transient surveys. So what you essentially are doing is probably you guys all know because, you pretty much work on transients, but, you take a picture of the sky tonight, and then let's say you take a picture of the same patch of the sky tomorrow, and then you compare these two images and essentially just subtract. And then if you get any remaining sources, those are new sources. So those are candidates for supernovae or anything like any explosive transients. And then what's plotted here is the area of, each of these surveys can cover. And then x-axis is the depth or how much you can go, how deep you can go. Essentially, that translates to the distance. And then it's you see a clear trend that if you want to go cover wider, you kind of have to go shallower. And if you want to go deeper, you kind of have to go narrower, which makes sense. And the leading surveys these days are called Atlas, and then also the ZTF. And then these guys are finding roughly 100 candidates per day. So that's roughly the discovery rate at the moment for supernova candidates. And then, but there's going to be a game changer, all you guys know, LSSD. And then it's gonna increase the sample size by at least 2 orders of magnitude. So you're gonna find 10,000 candidates per day. So it's going to be a tricky game. It's exciting, but it's also overwhelming. But I think that I just heard the news that LSSD camera had the first last night, something like that. So I think it's coming. It's happening. So we need to be prepared, but it's going to be an exciting time. So, you all, I guess all of you guys know what LCO is, but
No idea.
We have telescopes in South Africa.
in case you didn't know, it's a network of telescopes, robotic telescopes, so that you can use, even your smartphone to trigger your observations. And then I'm a part of this, something called Global Supernova Project that led by someone here. And I'm a core member of it. I've been a core member since I started here. So it's essentially we have more than 150 astronomers all over the world using more than 3,000 LCO hours to follow roughly 150 supernovae per year. And then this is complemented by the larger grand and space-based telescopes by the corporation. So my contribution at the moment is using these MMT and Magellan telescopes, 6.5-meter telescopes in Arizona and Chile, because I get access from the CFA. And then in the coming year, I'll get the access to GTC 10.4 meter because UF has access to it. So I want to combine all these resources starting from 0.4-meter telescope to 10.4-meter telescope. So I think that's going to be really exciting. And then I do some modeling as well to explain these transients. So what I use is something called Maser. This is also developed in Santa Barbara, like UCSB. So I use this public code to do the stellar evolution. So to get the progenitors of these core collapse supernovae. And then I use something called Stellar. It's a radiative transfer code. So you can actually get the, observables. So what if you explore this kind of progenitor, what would the light curve look like? That way you can actually compare with the observations and then extract the physical parameters from it. So this is what I do. And then during my PhD, I generated more than 4,000 supernova light curve models. So it's a huge grid. And then I'm now using this. I'm working with a student at Harvard to apply Gaussian process and to have a light curve emulator so that you don't have to run, these light curve calculation each time. So essentially encapsulating, between the parameter space. And so that's work in progress. So I think I want to get into the main science, but please feel free to ask questions anytime because I only have 20 slides. So if you guys don't ask me questions, I think I'm going to stop like really early. So I just want to talk about this 23 IXF that happened in M101. So, but before getting into that, I want to say something about the mass loss and then the circumstantial medium. So I said this path was predicted like 40 years ago, but we, really hadn't had this really convincing candidate. And then also what kind of star is actually going to core collapse supernovae, depending on the projectile mass range you're talking about, it's still somewhat uncertain. So the big question is what progenitors, die in what way? And then this is complicated by the fact that these massive stars lose quite a bit of mass before explosions. So these are really simplified pictures, but in reality, it looks more like this. So the progenitor is surrounded by this circumstellar medium, and then this CSM is produced in the mass loss activities before the explosion. So this remains to be the major source of uncertainty in the stellar evolution theory, but it has significant effects on the formation of supernovae and then also the compact objects. So it's a remaining, it's a really big question in the field at the moment. And if you see this plot where mass loss rate is the y-axis, and then x-axis is the expansion speed, and then each different colored regions corresponds to different kind of massive stars. And if you go to the right, you essentially have more massive and compact objects because expansion velocity roughly corresponds to the escape velocity of that progenitor. So, depending on what kind of progenitors you start with, there is more than 5 orders of magnitude in the mass loss rate. So this kind of illustrates, there is a wide range of mass loss rates. And if you're talking about red supergiants, so these are typical progenitors for the core collapse supernovae. And then something one example is the Betelgeuse, which has roughly 15 solar masses of mass. But if you're talking about something called luminous blue variable, something like Eta Carina, they go up to 100 solar masses. So there's a wide range of mass, projectile masses on, and that reflects wide range of mass loss rate. And then the idea is that coming back to this, picture that progenitors are embedded within this CSM. But once the supernova happens, the supernova ejector interacts with this CSM. And then essentially that means the supernova ejector traces this CSM outward. So if you can use this to actually trace the mass loss history in reverse. So you start with the most inner region and then goes outward and outward. So that traces the mass loss history in reverse. So you can use this as like a time machine for the mass loss history. So that's really interesting. And then that's what I meant by using supernovae as tracers of late stage stellar evolution. So the big question here is, if you use supernovae to infer these mass loss rates, what would they end? Yeah, where would they end up in this plot? So now I'm going to get into like this detailed case study of 23IXF. Does anyone know which point source is a 23XF? Yeah, it's this guy. Obviously, it's this guy. And this was a type 2, meaning that it was a hydrogen-rich supernova that came from a red supergiant. And then it was really nearby, and then fortunately, the first detection was only roughly 3 hours after explosion. So we got it really early, and then the guy who did it is this legend called Koichi Tagaki. So who's an amateur astronomer in Japan who has his own network of small telescopes in Japan, like 3 different sites, totaling 6 telescopes. I think pretty much like 50-centimeter telescopes in Japan, and he remotely controls them. So it's like a mini LCO network run by a single person. So that's quite amazing. And then this was actually Friday evening in the US. So I was drinking at the bar, but for some reason I was checking my emails, and then I got an email from him like 2 minutes ago, and then I saw it. And wow, this is exciting. And then the bar for some reason had Wi-Fi, and I had my laptop for some reason. So I just like immediately plugged my laptop and then triggered LCO observations. So this is also like, really the advantage of using LCO networks. You can just trigger the telescopes from anywhere, even from a bar. So, you can pretty much trigger from anywhere. So this really demonstrates the power of LCO. And what's interesting is that it was so nearby. The galaxy is really nearby at roughly 6 megaparsecs. And then it's a really beautiful face-on galaxy. So it's a really popular target for many astronomers. So if you look at the archival images of the same location as a supernova, you find a bunch of HST, Spitzer, and many ground-based telescope images. So you can actually identify the progenitor itself that later exploded as this 23XF. So you get detections in multiple filters. So that's quite amazing. And if you construct SED from it, this is what you can write. So this is the flux in y-axis and in the wavelengths on the x-axis. So the actual observations of 23XF are these red points. So if you compare with a vanilla red supergiant that has no CSM, this is the SED that you'd expect. But for this 23XF, it was much redder. So you kind of have to incorporate this dust component that's plotted as this red curve. And then if you add this red and red supergiant component, that's the green line. So that roughly produces the SED of the observation. So this means the progenitor was really dust enshrouded by the CSM. And then what's more exciting, I think this was the first time that was observed. So you actually had an excellent timeline, cadence observations of the progenitors. So you can plot its flux in 4.5 and 3.6 microns. Those are blue and red, points. So you kind of see the periodic variability which has the period of roughly 1,000 days. And then what's plotted in the background as these gray points are the observations of the Betelgeuse. So compared to the variability of the Betelgeuse, the progenitor of 23XL has this, was doing something crazy in the last, more than 10 years before the explosions. So I think this was the first time that we could actually get these detailed views of the progenitor itself. And then using this information, you can infer the physical property of this progenitor. So it was reddened, so it requires roughly 10 to minus 4 solar masses per year of mass loss before explosion to have this amount of CSM that's enough to reproduce the SED. Oh, yeah, please.
Does your model assume that the CSM is spherically distributed?
Yes, and then yes, but this is not my model. Yeah. Yeah.
Understand.
Yeah. Yeah. So this is assuming, spherical distribution of CSM. But it was unlikely because I'm not going to show this plot, but there was also parametric measurements that has, roughly 1% of polarization in the early phase. So that likely means the actual CSM distribution is more like a football shape. So this is a really simplified pictures. Yes. And then, as I mentioned, you see this periodicity, which roughly has 1,000 days of period, and then it was a red supergiant. So we have a really good idea of what the progenitor star was in this case. And then, so this is, my work coming. So I'm going to talk a lot about these light curves. So these are essentially brightness as a function of time. So the brightness is on y-axis, and then the time is the x-axis. And then different color symbols corresponds to different filters. So which color you are looking at, from UV to near infrared. And then what's amazing about this object is these white open places are amateur observations. So, it roughly started -10 in absolute magnitude, and then it rose up to -18. So it rose 8 max in the first 5 days. So it's a really rapid evolution. So the rise is well captured. And then to me, what was most interesting was that if you look at the U minus B, so this is the color. So if you're comparing the brightness in 2 different filters, and then if you plot that U minus B, so the color becomes bluer as you go down. And then again, the x-axis is the time after the first write of this supernova. And then you see this dip. So initially it was getting hotter or bluer in the first 3 or 4 days. And then it became redder. So in a really simple picture of supernova, when the shock wave reaches the surface, that's the first light you'd see, and then the supernova ejecta just, expands and cools down. So essentially, you just see the red color evolution. But in this case, for the first few days, we actually saw this blue-white evolution. So what's going on? So this doesn't look a typical evolution for core collapse supernovae. So coming back to this picture, I think what happened is that the progenitor, again, from the progenitor detection itself, we know it was really embedded in this dense CSM. And then the photosphere of this, after the shock breakout, the progenitor itself actually formed within the CSM. So the CSM was substantial, so the photosphere can actually form inside the CSM. And then this early first 3 days or so, you're actually seeing the photospheric evolution within the CSM. So that's something called delayed shock breakout. So this CSM could act as an extended envelope in a sense. And then until it breaks out of this dense CSM, you see this blue-white color evolution, because essentially this interaction kind of acts as the internal heating source that provides the heat to the photosphere, and then you'd see this blue-white evolution. So this is really indicative, as I said, a delayed shock breakout when you have this dense CSM. So if that's the case, you can use this time scale of how long it took for the evolution to transition from blue to red well. which was roughly 3.4 days. And then if you assume, let's say a typical, supernova ejecta shock velocity of 10,000 kilometers per second or so, you can estimate this radial extent of the CSM just by saying V shock times TUV. And then that roughly corresponds to 3 times 10 to 40 centimeters or 4,000 solar radii. So this typical red supergiant has a radius of roughly 5 to 1,000 solar radii. So this 4,000 is much bigger than just a bare photosphere of the red supergiant. So this again indicates there is something, outside of the progenitor itself, which corresponds to the CSM. So then, given this information, you can try to model the light curves. So what's plotted here is the pseudo-bolometric luminosity. So you integrate from the U band to I band to get the luminosity. And the x-axis is the time. And then in this case, I'm just showing the supernova light curves without including any effect of CSM interaction. And then, points are the data. And then these colored curves are color-coded. Colored curves are the model light curves, color-coded by the explosion energy of the supernova. So this is like a reasonable range, roughly 1 to 2 times 10 to 51 arcs. So that's a really expected range for the explosion energies of these core collapse supernovae. But even if you use, 2 times 10 to 51 arcs of explosion energy, you can't really reproduce the peak. So you're missing something here, which is the CSM interaction. So here, I'm showing the models now including the effects of CSM interaction. So that's how the model light curves are color-coded by this mass loss rate that produce the CSM. And so from the progenitor observations, people have estimated this mass loss rate to be 10 to minus 4 up to a few years before the explosion. But those are the purple lines, purple-ish lines. But again, this mass loss is still low to have the effects, any noticeable effects on the light curve evolution. So you kind of have to, need to put somewhat crazy amount of mass loss, like up to 1 solar mass per year. That's huge. You're losing a solar mass. You're losing sun in a year. So it's insanely huge. But those models, not perfect, but roughly produce the peak luminosity. So I think this is the ballpark estimates that we are talking about. So to have this kind of CSM, you need really extreme wind or maybe outbursts, mass loss outbursts that had this range of mass loss, 0.3 to 1 solar masses per year, and then in the last 2 to 1 year before the explosion to reproduce the radial extent of the CSM. So stars are doing something crazy right before they die. So these are the recent findings. We have some more, supernovae that show that kind of indicated this. So coming back to this plot of mass loss rate as on x-axis and then expansion speed on, mass loss rate on the y-axis and then expansion speed on the x-axis. So if you plot the red supergiant progenitor of 23XF, it was roughly here.
Oh, whoops.
Yeah, but if you actually use the supernova to infer the CSM, so let me back up. So these progenitor observations were only up to 3 years before the explosion. So it's more quiescent phase in a sense, but the supernova actually proves really the last moment of the progenitor evolution that roughly corresponds to 1 to 2 years before the explosion. So, and then it, place itself is, roughly here in this plot. So there is a huge jump.
So did this crazy mass loss happen in the last 3 years?
Something like that, last 1 to 2 years. So, which we don't really understand. That's why
Beetlejuice doing that, we know it's going to explode in 2 or 3 years.
Finally.
But yeah, probably might be a good indication. But as I showed in the previous plot of the progenitor, observations, the Betelgeuse, sorry?
surprisingly human timescale.
Yeah.
Yeah. Yeah, so that's really exciting. Yeah, that's a good point, but I'll come back to it. Yeah, so this is really the takeaway message that there is a huge discrepancies between the Maslow's estimates in the last few decades from stellar evolution, which, predicts somewhere here, which, more or less consistent with the progenitor observation of 23 IXF, but in the last years, it's doing, these stars are doing something really crazy. And then these are recent findings that, we just got. And then, who knows what's causing this mass loss? So that's a big remaining, that's a big question. That's a really big ongoing debate. What could cause this crazy mass loss? It could be like internal gravity waves in the progenitor itself that is induced by some, instability in the nuclear bonding that's propagated to the envelope. So, maybe you could have some kind of outburst activities before the explosion. Or maybe, these massive stars are mostly in binary system. So if you have binary system, then maybe you could lose quite a bit of mass from the binary interaction. So, and, there are other models, but I think we are still trying to figure this out. And this is just a single object. So, this sounds like it merits a sample study. So that's my next section. So we did sample study, but before getting into that, I want to introduce this type 2 supernovae. So they are called type 2 because they're hydrogen rich. And then 2N corresponds to narrow emission lines in the spectra. So if you look at the spectra of these type 2N events, you see these narrow emission lines of hydrogen, like Bowman series, H alpha and H beta. And then the width roughly corresponds to 1,000 kilometers per second or so. So this is about an order of magnitude smaller than the ejector velocity of the supernova, which is roughly 10,000 kilometers per second. So the picture I want you to have in mind is that something like this again. So the supernova happens within this dense CSM that in this case, photosphere essentially continuously formed within the CSM. So the emission that you see is really the shock layer of the supernova ejecta and then the CSM. And then the CSM is dense enough that can decelerate the supernova ejecta. So this width corresponds to the velocity of this, interacting shell, which has roughly on the order of 1,000 kilometers per second. So since you're seeing this photosphere formed at the shock interface of the supernova ejecta and then the CSM, you don't really see what's inside the photosphere, which is essentially the supernova ejecta. So we don't really have direct evidence of what's exploded within the CSM. So that's a big uncertainty for these interacting supernovae. And then if you look at the light curves, it's kind of mess. Yeah. So it spans 5 magnitudes in the magnitude space. So that's roughly exactly like 100 times in flux space. And then the time scales also spans tens to hundreds of days. So it's a mess. And then we know it's a heterogeneous class. So they show heterogeneity in observed properties. And then this likely reflects the diversity in the progenitor and or CSM properties. And this was done by PTF sample, which had 40 supernovae in it. But does this really span the population? So I think this was the main motivation to run an even larger sample study. Now that we have public survey, ZTF, Atlas, and Gaia, and then also people report the classification publicly. So you can compile the list of publicly classified SN2N, and then you can get the public photometry from ZTF, Atlas, and Gaia. So, and then for each object, you can get, light curves like this, where different color symbols correspond to different filters from ZTFG to ZTFI. And then what we did is using the 2D Gaussian process to interpolate between the data points, both in the time and in the wavelengths, so that for any given epochs, you have SED information. By doing so, you can do uniform measurements on the Gaussian process light curves. So what we did is really simple. So this is showing the flux evolution in the rest frame. And then you just measure the peak flux and then measure the rise time, let's say from 50% to the peak on the rise time. And then also like, from the peak to the 50% flux on the decline. So you can measure these time scales at every 10% increments. So we did this uniform measurement so that, it's comparable. And then when we will model these events, you can actually, do the direct comparisons with the model. So these are really a simple set of measurements. And then since you have SED information at any given epoch, you can integrate over the wavelengths to get the luminosity. So that's what's plotted here as the optical, where you integrate over the optical wavelength range, and then the biometric when you integrate over the full wavelength range. And then you do the same measurements, find the peak in the luminosity, and then measure the rise times and the decline. So once you have that, you can plot all of them in a single plot of the measurements. So y-axis now is the absolute peak brightness in R band, and then the x-axis is the redshift. So this just shows the sample distribution. And then ZTF, Atlas has limiting magnitude, survey limiting magnitude of 19.5, where ZTF has roughly 20.5 of limiting magnitude. So these new sample, which are plotted as the black squares, are above that limiting magnitude. So this is really limited by the survey depth. And then these really high redshift events come from previous survey from Pansters, where they went much deeper, down to like 23.5. So that's the sample distribution, but PTF have, 30 or 40 supernovae in it. But our sample, which in this plot I call narrow, has more than 400. So thanks to these, public surveys, we could have a sample increase, like more than order of magnitude increase in the sample size. So now I call this as the largest sample study of interacting supernovae. And then you can plot all the Gaussian process light curves in the luminosity space. So again, it's heterogeneous that they span wide range in the peak luminosity and then also the time scales. But if you squeeze your eye, you might see maybe two populations. Like this is a denser region with the faint and more fast evolution, and then there might be more luminous and longer duration light curves. So maybe there are two populations. I'll come back to it. So if you plot, now you plot peak luminosity as y-axis, and the x-axis is the time scale, measurements from 50% on the rise to the peak, plus from the peak to the 50% on the decline. So that's what's plotted as x-axis. Again, the time scale spans roughly an order of magnitude. And then the peak luminosity spans roughly 2 orders of magnitude. So yeah, it's heterogeneous, but it's not a really tight correlation, but you see overall correlation where you see more luminous events having longer durations and vice versa. So overall peak luminosity and time correlation. But if you rotate the sample along this correlation, this is what you'd get. So you rotate the sample along the correlation around this medium time scale and then the median luminosity. This is the distribution you get. So essentially, the difference in the y-axis corresponds to the distance from the correlation, and the x-axis corresponds to the distance from the median of these luminosity and the time scale. But what's interesting here is this distribution. It looks like distribution might be bimodal along the correlation. So if you have a uniform distribution, you don't expect to see this, but there might be something going on here. And you can plot this better. So now the previous plot, I have luminosity and the time scale. But now you can get the radiated energy, which is essentially you integrate the luminosity over time scale. So this is essentially L times T. So Y times X in the previous plot. And then what I'm now plotting as Y-axis, sorry, X-axis is the average luminosity above 50% flux space, so that I can plot the characteristic time scale as diagonal lines. Because this radiated energy is this average luminosity times this characteristic time scale. So you see, and then so there are these populations that is more luminous and they have longer duration of roughly 100 days. And then there might be this subpopulation on the fainter end, which has roughly 30 or 50 days of time scale. And then you clearly see this bimodality in the radiated energy distribution, which stems from the previous plot, where we see the bimodal distribution along the correlation. So this, I didn't expect to see this. So this is a really main finding of this work. So now if you use this median, radiated energy to split the sample into two, then you can find the median light curves of each class. So the orange ones have radiated energy smaller than this median value. And then this blue light curves is the median light curves of all the events that have radiated energy greater than the median. So you clearly see this separation in the light curve evolution, which I kind of hinted in the first plot, but this is the, faster evolving, less luminous light curves. And then these are the slowly evolving more luminous light curves. And then the median light curves only overlap at the 2 sigma level. So it seems like, although it's a heterogeneous class, you see these two major populations. So, and this is what I essentially just said. So this bimodality clearly separates the light curve morphology into two. One I call luminous slow, and then the other I call faint and fast. So takeaway is that they are heterogeneous, but yet bimodal. So it looks like it may be the case that there are two major progenitor under CSM formation pathways to form these interacting supernovae. So to do some math, you can get this, high energy peak corresponds to 2 times 10 to 50 arcs, where this low energy peak corresponds to roughly 10 to 49 arcs. And then, let's just assume this radiation is produced by the shock interaction that converts the kinetic energy of the supernova into radiation. So, and then this efficiency of combining kinetic energy into radiation is roughly 10%. So if you do that for the high energy peak, you get the kinetic energy of 10 to 51 arcs or so. So that corresponds to the exposure energy of the supernova. So this is more or less like the vanilla value for what you'd expect for core club supernovae. But what's interesting for the low energy peak, that's roughly in the order of magnitude lower. So which corresponds to 10 to 50 arcs. So this sounds really low. So it might be the case that, there is a substantial, population of low exposure energies embedded in, just in this population. So that's really interesting. And then I'm now doing the, numerical modelings of these light curves to actually pin down the supernova and then the CSM physical properties. So that's work in progress. But for the supernova forks, there are something called fast transients. And then if you plot this 1BN from Griffin's paper in 2017, he did the sample analysis. So you can compare the light curve templates of 1BN to our 2N templates. So the type 1BN has really fast evolution compared to type 2Ns. And then if you shift all the light curves to the peak, and then you can compare with other kinds of fast transients. So this is again 1BN in the purple shaded region. And then there are this new class called 1CN. So these are more stripped progenitor that doesn't show any sign of hydrogen or helium, but interacting with the CSM. And then those are these yellowish, points. And then there are more mysterious class of fast transients, where prototypical one is 18 cow. People are very excited, got excited by the name itself, cow. And then it has a really fast, much faster evolution. So I think we are seeing the continuum more or less in the, what kind of CSM you interact with, which course, which reflects the project environment. And then the type 2N have longer duration. And in the time scale that's not spanned by the 2N, these more stripped envelope interacting supernova nicely fills in. So 2Ns are slower than fast transients with evidence for interaction with hydrogen post CSM. So I think this is interesting. And then we're going to find out more once we have a large sample of these guys. So now I'm running a HST program to get the host galaxy images of these interacting supernovae in the rest frame UV, because the UV traces the star formation, more recent star formation, because the UV emission comes from massive stars. And then we got 202 snapshot orbits over the current cycle to the next cycle. And then it's a snapshot program, so the execution rate is not 100%, but we shorten the exposure time of each observation enough that I think the expected execution rate would be like 60% or something. So we still get more than hundreds of these observations. And then what you can do is something like this, where I'm just plotting the previous study, let's say. So this red circle corresponds to the location of the supernova. And then this is the host galaxy. And then this purple dotted circle shows the 90% flux radius of the galaxy. So so essentially, HST is so great that HST spatial resolution is so great that you can actually resolve the local environments of the supernova. And then you can compare that properties with the global properties of the host galaxy. So you can do something like this, where fractional flux means the flux at the UV flux at the supernova location divided by the highest UV flux within the host galaxy. So this traces the star formation rate in a way, because you expect more UV flux at more star forming region. And then what's plotted here has these lines are the different types of transit of supernovae. So like quark lap supernovae is plotted as this brownish curve. And then like something called super luminous supernovae, as the name suggests, like really luminous supernovae, like they show distribution something like this. So for these ones, they track star formation really well, but for these ones, for some reason, they don't really track the star formation rate. So this is a really exciting field. And then you can also measure the offset from the host nucleus. And then, so essentially this is more or less the measurements of clustering. And you can, compare that distribution with a, let's say, exponential disk or something of host galaxies. And then this shows how this distribution trace the clustering. So, but this has never been done for interacting supernovae. So this is where my program, plays a role. And this is showing for a sample of interacting supernovae, it's a redshift distribution. And then number of objects that have archival images of HST. So these are the blue ones. And then this orange distribution is our proposed sample. And this is showing now x-axis is the peak absolute magnitude of the supernovae. And then again, this blue distribution is in the archival sample, and then this orange is the proposed. So our sample spans wider range in the parameter space, and then also 7 times increase in the sample size. So once we get all of these observations and then analyze them uniformly, I think we can place interacting supernovae on these two plots, and then compare with other types of supernovae to see, how much they track the star formation rate or clustering. Maybe it's the case that, I don't know, this is just my naive prediction, but the more luminous and slowly evolving events might track star formation better compared to the fainter and less luminous events. But that's it. And how much time do I have? Like,
10 more minutes until the
but I want to have some time for questions. So I'm just going to go quickly over this. So, as I mentioned, LSSD is coming up, and then one example of study we can do is actually, do more statistics on the electron capture supernova, let's say. So I worked with a student to come up this robust color diagnostics. So this is showing the density profile as a function of radius for different progenitors. So SAGV stars are expected progenitors for electron capture supernovae are plotted as these solid lines, and the red supergiants, expected progenitors for more typical cochlear supernovae, are shown as these dotted lines. So there is a substantial difference in the density distribution of the progenitors that results in different color evolution in the supernova phase. So iron core collapse from red supergiants are plotted here, while the electron capture supernova models from SAGB stars are plotted here. So you can roughly place a line that divides these two populations. So you can use this color diagnostic on a larger sample, let's say from LSST. We're actually trying this with ZTF, and then in the future we can apply this method to ZTF. But 18ZD, that's the electron capture supernova we published a paper on, nicely places itself on the electron capture supernova regime. So this is another, line of support that it was indeed an electron capture supernova. And then quickly, I'm going to talk about this supernova precursor emission. So the emission before the supernova itself. So I'm just showing the light curves of type 2N. So this is an interacting supernova. And then it has these crazy light curves like double peak. But what's more interesting is that if you, after the fact, you find a supernova, you go back in the archival data to see if you could identify any precursor emission before the supernova. And then we actually found one. So this is on the scale of from 400 days before explosion. So, and then it's a really long duration and then faint evolution. Sorry, faint and gradual rise in the luminosity. And then when supernova happened, it just, skyrocketed, like just boom. But, depending on these observed properties, you can, put this in the LSSD simulation and then see how many of these you'd expect to see in the actual observations. So I worked with a postdoc CFA to do this. And then don't worry about the details, but we expect to observe 100 detections per year with LSST, because LSTs go much deeper than the current survey by roughly 4 magnitudes deeper. And then since these are long duration events, so you don't really have to worry about the cadence. So the LST is really great for finding these. So now the question is, can we find these in real time from the observations? So you can probably write a custom filter. So let's say you can now reverse the question of before actually detecting a supernova, can we identify this precursor in real time? And then if so, we can get the spectroscopy during this precursor phase so that you can actually study about the kinematics and then the chemical compositions of these outbursts themselves. So I'd like to use 10.4 meter because this is going to be really faint. And then if supernova happens, that's amazing. So, you might be able to, so this is coming back to, somewhat Chris's question on seeing the project activities. Can we say when this starts going to explode? It's a long shot, but it's worth it. And then we are now running this precursor bot. So it's essentially filtering these, potential candidates on the ZTF data stream. And then it's showing that. And then this has, so we did a host galaxy association first so that you can get the distance. And then that way, the luminosity range of these precursors. And then we do the cut of anything longer than 50 days on the duration. And then this way you can try to identify these events. This is still work in progress. And then, in the future, it'd be good to have a Tom rather than just Slack monitor these events. So that's where I'm most interested in developing once I move to UF. So, and then this is showing like, reconstructed density profile from the light curves. And then you can actually trace this, you can convert this density distribution to the Maslow's history of the progenitor. So the idea is to get spectra during this phase, so that you can actually study the mass loss. So I think that's another thing that we can do with LSSD. So that's exciting. So I'm just gonna put the summary here. Supernovae, they're stellar endpoints with wide-ranging implications. And global supernova project is great for follow-ups. And I'm using Mason Stellar for modeling. And then the main parts that this really detailed study of 23XF shows extreme mass loss activity of up to 1 solar mass only in the last year. And then the big sample of interacting supernova shows heterogeneous yet bimodal distribution of the radiated energy. And then coming golden age with LSSD, we can do better statistics on electron capture supernovae. And then also we can try to identify supernova precursor emission in real time. So I'll just finish with this. Thank you so much.